Hello friends, welcome to H2 Event Academy. In this particular lecture, we will discuss about the Stokes Theorem. So let's begin. So the Stokes Theorem gives a relation between the line integral and the surface integral. Okay. So for understanding this, let us recall our discussion on Green's Theorem. What we have seen in the Green's Theorem. Suppose we have a curve C is bounding a region R. Then using the Green's Theorem, we have m dx plus n along the curve C equal to surface integral along the region R del n upon del x minus del m upon del y dx dy. The basic restriction on the Green's theorem is that it is only applied on the planar region. There should not be any term of z. The restriction here is applied on planar region. There should not term. But such restriction is not there in case of Stokes theorem. Restriction not there in case of Stokes theorem. That is, the Stokes theorem can be applied in three-dimensional space. Be applied in three-dimensional. But Green's theorem is applied only in planar region. Planar. Okay. Now let us understand this with the help of a diagram. Let us understand the Stokes theorem. Let us take a surface. Let us take a surface, and this surface S is being bounded by a curve C. Let us draw the curve C. This is our surface, our curve C. Curve C is bounding the surface S. So we have the basic expression for the Stokes theorem is, let us consider f as a vector point function, and we have our surface as the unit vector along the outward normal is in this particular. Basic expression for the Stokes theorem f dot n. Basic expression for the Stokes theorem is f dot dr along the curve C equal to surface integral along surface S, curl of f dot n cap into our line integral, and this is our surface integral. The Stokes theorem gives a relation between the line integral and the surface integral. Now let us take the coordinate axis line. This is basically the surface integral. We have already seen the lecture of the surface integral. For taking the surface integral, we take the projection of this curved surface on the xy plane. The xy plane in particular, we can take projection on any of the plane based on the demand of the surface integral. Let us take the projection on the xy. Our project. This is our curved surface. Let the projection is a region R. You can further simplify as. Let us take the unit vector perpendicular to this region R is k cap. Let's consider angle between the n cap and k cap is gamma. So we have ds cos gamma equal to d. Here ds is equal to dr upon cos gamma. Cos gamma we can write as cos gamma is equal to cap dot. This is equal to dr upon cap dot. Let us further simplify this. We have f dot dr along the curve C equal to surface integral along the surface S, curl of f dot n cap. ds is dr upon cap dot. This is the basic structure of the Stokes theorem. Step is unit vector along the outward normal. ds we can found using the r, which is projection of the curved surface. C is traversed in a positive direction. Using the right hand thumb rule, we can find the direction of this. We can find the direction of the curve. Here, outward normal is in this particular direction. This curved C is traversed in a anti-clockwise. So let us start discussing the problems on the Stokes theorem. Let's start discussing problems. So let us start discussing the problems one by one. Okay, so what is given in question number 1? Prove that r dot dr along the curve C is equal to 0. We have in question number 1, we have to prove that line integral along the curve C r dot dr is equal to. Let us solve this. So we have from the Stokes theorem. So we have, let us write down the expression for the Stokes theorem. So we have f dot dr line integral along the curve C is equal to surface integral along the surface S. We have curl of f dot n cap into ds. So let us consider. Let us take f as, let f is equal to r vector. Let us put this in equation 1. We have r dot dr along the curve C equal to surface integral along the surface S, curl of r dot n cap into ds. And from vector identities, we have curl of r equal to 0. This is as per the vector identities. Vector identities. As per vector identities, curl of r is equal to 0. This particular term, curl of r is equal to 0. This means this whole expression is 0. This means r dot dr along the curve C equal to. Okay, now let us discuss question number 2. How we can solve this? Let's discuss question number 2. Okay, what is given in the question? Prove that line integral, question number 2, line integral along the curve C, this is phi times of del psi dot dr equal to minus of phi times of, sorry, this is line integral along the curve C, this is psi times of del phi dot. How we can solve this? Let us write down the Stokes theorem. Okay. So we have the Stokes theorem as f dot dr along the curve C equal to surface integral along the surface S. This is curl of f dot n cap into ds. So let f is equal to, let us consider, let f is equal to del of phi into psi. So this we can expand as this phi times of del psi plus psi times of del phi. Let us place here, let us place the value here. We have phi times of del psi plus psi times of del phi dot dr along the curve C. This is equal to surface integral del cross curl of f. We have del cross phi times of del psi plus psi times of del phi dot n cap into. So let us expand this. This is equal to surface integral along the surface S. We have del cross phi times of del psi plus del cross psi times of del phi dot n cap into. So from vector identities we have curl of phi a, curl of phi a. Where phi is a scalar and a is a vector quantity. This is equal to del phi cross a plus phi times of del cross a. Okay, here del psi is gradient of psi. Gradient of psi, psi is a scalar quantity and gradient of psi is a vector quantity. Similarly, phi is a scalar quantity. Gradient of Gradient of phi is a vector quantity. So on comparing this, is our A vector, also A vector. Okay, so let us apply this vector identity on this. So we will get the result as this is equal to surface integral along the surface S equal to del phi cross del psi plus phi times of del cross del psi. This is the expansion of this one. Similarly for this one, this plus del psi cross del phi plus psi times of del cross del phi. Okay, dot n cap into, and this is del cross del psi. This is gradient of, sorry, this is curl of gradient of psi. This one is curl of gradient of phi. So from vector identity, curl of gradient of a scalar function is 0. So this is 0 and this is also 0. Okay. And this is del phi cross del psi. This is del psi cross del phi. Let us change the order. There will be a minus sign, minus of del phi cross del psi. These two terms are same. The whole expression will be 0. So since this whole expression is 0, this expression will also be 0. Just place 0 here. Just place 0 here. So equal to 0. So this means line integral phi of del psi along the curve C dot dr plus line integral along the curve C psi del phi dot dr is equal to 0. Line integral along the curve C phi times of del psi dot dr equal to minus of line integral along the curve C psi del phi dot d. This we have to prove in question number 2. Let us discuss question number 3. Let us discuss question number 3. How we can solve this? Question number 3. Okay, we have to prove that tan integral along the curve C phi times of del psi dot dr is equal to surface integral along the surface S. This is del phi cross del psi dot n cap ds. How we can solve this? We have to show that question number 3 part A. So equal to tan integral along the curve C phi del psi dot dr is equal to surface integral along the surface S del phi cross del psi dot n cap into. Let us solve this. So from Stokes theorem we have f dot dr along the curve C equal to surface integral along the surface S. This curl of f dot n cap into. So let f is equal to phi of del psi. Let us place the value here. This is equal to phi del psi dot dr along the curve C. This is equal to surface integral along the surface S. Curl of phi times of del psi dot n cap into. Let us expand this. This is curl of phi times of del psi. This is equal to surface integral is del phi cross del psi plus phi times of del cross del psi dot n cap into. This is 0 because curl of gradient of psi is equal to 0 from vector identity. We are left with this particular expression. Surface integral along the surface S del phi cross del psi dot n cap into the value of line integral along the curve C phi times of del psi dot dr. Okay, now let us discuss part B. So for this, let us replace psi with phi. Phi curl of gradient of phi is equal to 0. We are left with this one. We are left with del phi cross del phi dot n cap ds, and the cross product of same vector is equal to 0. Okay, so these two are same vector, del phi and del phi, so equal to 0. So we have phi times of del phi dot dr is equal to. Now let us discuss question number 4. By Stokes theorem proved that divergence of curl of f is equal to. Let us solve this. Question number 4. Question number 4. Okay, so we have to prove that divergence of curl of f is equal to 0. Let us solve this. So let us take a volume V. Let us take a volume V that is being enclosed by a surface S. Let us take a volume V that is being enclosed by a surface S. Let us take a elemental surface ds here. So let us write down the solution. We have solution. Let V the volume closed by a surface S, and f be a continuous vector point function. So from Gauss divergence theorem, we have divergence of f dv volume integral is equal to f dot n cap into d along the surface. This is thus expression for the Gauss divergence theorem. So let us replace f with curl of f. Let us put this in equation. Let us take this as equation. Divergence of curl of f dv along the volume B equal to surface integral as curl of f dot n cap into. Okay, so now let us divide this whole surface into two parts. This will be like this. Okay, okay, so this is, let us take this surface as S1, the bottom surface S2. Since the n cap outward normal is in this particular direction, okay, so order of this curve will be in anti-clockwise direction. Okay, for this surface S2, we have n cap in this particular direction. Order of this will be in clockwise direction. This and this curve, this is curve C and this is curve C, because we have cut it from here so that it get divided into two surfaces S1 and S2. So the curve C is same for the surface S1 and surface. This S is equal to S1 plus S2 equal to surface integral along the surface S1 curl of f dot n cap into ds, okay, plus surface integral along the surface S2 curl of f dot n cap into. Let us write down the expression for the Stokes theorem. From Stokes theorem, we have f dot dr along the curve C equal to surface integral along the surface curl of f dot n cap into. Okay, so using Stokes theorem, this is our curve C. Curve C is same for both the surfaces. This is for the, this expression is for surface S equal to, using Stokes theorem, this is equal to tan integral along the curve C. Okay, so this is positive because this is in anti-clockwise direction. Anti-clockwise. this is clockwise. This will be negative. This will be positive. Tan integral will be positive in the case of surface S1 and it is negative in case of surface S2. This is equal to along the curve C. This is f dot dr. This is minus of, because this is a clockwise direction. Along the curve C, dot, this curve C is same for both the surfaces, because surface S1 is being enclosed by the curve C. Similarly, surface S2 is being enclosed by the curve C is same in the both the cases. In the case of S1, it is in anti-clockwise direction, but is in the case of S2, it is in clockwise direction. This expression is negative, and this expression, both will cancel out each other. So the result is 0. So this means divergence of curl of f dv is equal to 0. Hence we can say that divergence of curl of f is equal to, okay. Now let us discuss question number 5. By Stokes theorem proved that curl of gradient of phi is equal to 0. Okay. Let us discuss question number 5. By Stokes theorem proved that curl of gradient of phi is equal to 0. For 5, we have to prove that curl of gradient of phi equal to, let us write down the expression for the Stokes theorem. In Stokes theorem, we have f dot dr along the curve C equal to surface integral along the surface S, curl of f dot n cap into ds, that f is equal to gradient of phi. We have gradient of phi dot dr along the curve C equal to surface integral curl of gradient of phi dot n cap into, let us calculate gradient of phi dot dr. This we can write as gradient of phi, we can write as I del phi upon del x plus j times of del phi upon del y plus k times of del phi upon del z, dot product with dr we can write as dx I cap plus dy j cap plus dz k equal to del phi upon del x into dx plus del phi upon del y into dy plus del phi upon del z into dz. This is equal to total differentiation of phi. Okay, so the gradient of phi dot dr is equal to d phi. Okay, so this we can write here equal to tan integral along the curve C d phi equal to surface integral along the surface curl of gradient of phi dot n cap. This we can write as phi. The integration of this is phi. And limits, let us place the moment. Let us take the curve C as closed curve. Let us take a point A, the starting point, and since it is a closed curve, so the starting point and end point is same. The limit will be A, and starting point is A and end point is, this is equal to surface integral along the surface S curl of gradient of phi dot n cap into d. The starting point and the end point is same, so this is equal to, this is curl of gradient of phi dot n cap ds is equal to 0. This means curl of gradient of phi equal to, okay. So we have discussed up to question number 5. We will discuss further questions in next particular lecture. Thank you.